Hi, this is joint work with Flavio Junqueira and Idit Keidar, done mostly during an internship with Yahoo Research. Um, this is a bit higher level. We have today these huge data centers we keep mentioning that run web applications by different customers, and these customers require the data center to handle changing loads, often rapidly changing loads, but they do prefer to have isolation, from other customers and other services running together with them. Now, we need, in order to accommodate this changing load, we need to have reserves machines, so machines waiting for a customer, ready to handle rapidly changing load or load spikes. What we'll talk about here is how to share these reserves by using preallocation without breaking isolation or getting customers worried about isolation. So I'll talk a bit about how we model the data center and the applications coming. So applications are comprised of services, like separate services or tiers, front-end, business logic, etc. And each of these is comprised of a set of virtual machines that need to run. So these are separate independent virtual machines. We have virtual machines of service 1, virtual machines of service 2, and so on. And the structure of the data center is that it has many physical machines that can run these VMs. It has the image storage, where the images are wherefrom the images are loaded to the physical machines. There is a load balancer that has to direct requests to the actual PMs that currently running the VMs of the service that the request is destined to. And we have an orchestrator that has to manage all this, boot machines, update the load balancer, and so on. And we draw it like this. We have the image store here, so we load images to the physical machines. Each physical machine is the blue rectangle. And we have a virtual machine. VM1 is the virtual machine of service 1, VM2 is the virtual machine of service 2, and we don't mind here whether a service belongs to one customer or another. Service is a service. And incoming queries arrive at the load balancer directs them to the correct physical machine, and they arrive at the virtual machine and are handled. Now, this gives us great isolation because we have a single virtual machine running on a single physical machine, so perfect isolation, no contention on anything. But there is no flexibility. Like every physical machine only handles requests to the virtual machine it's currently running. Second option is running multiple virtual machines on every physical machine. This works very nicely flexibility-wise, but we don't get isolation. So supposedly the hypervisor promises us perfect isolation. We get our CPU, our allotted CPU as necessary, and no issues arise, but there are some issues that might arise, like back channel attack vectors that allow us to realize what the memory accesses of VM running concurrently with us, and contention on bandwidth of internal storage. And these are not yet and not always handled perfectly by the hypervisor. So clients are sometimes reluctant to run together with other services, and especially with other services of other customers that may have different standards for security. And they prefer to run alone. They want their VM to run alone on a PM, their virtual machine to run alone on a physical machine. And now about load and about how allocation is done. So the load of these services generally follows a diurnal cycle because the requests arrive from clients who wake up in the morning and go to sleep in the evening. And so in during the day the load is higher and during the night the load is lower. We don't address these issues, but sometimes there are load spikes. Suddenly a lot of clients, a lot of accesses to a certain service, and we focus here specifically on the issue of flash crowds. Or suddenly your service or your application is mentioned on /dot, and you get 200 times your usual load, and exactly that's the exact time where you don't want to fail. This is when you want to handle all your load. So we need to, the client, the customers, they want to be ready for these loads. However, allocation takes time. We need to take the image from the storage, put it on the physical machine. We need to bootstrap the virtual machine. This takes time, in the order of minutes. And that's why customers run reserves machines for spikes. Side note, we're not handling here the issue of sleep modes. Separate, independent issue. So, like I said, the classical approach, we run more machines than we need per service. Most straightforward approach is what we call slack factor allocation. You have a slack factor we denote by alpha, and if you have a load of W, meaning you need W machines to handle your load, then instead of allocating W machines, let's say 4, you allocate alpha times W machines. If alpha is 2, then you allocate twice as many machines as you currently need. And the fact is that most of these machines are idle most of the time. They're reserves. You don't need them. So what do we do with preallocation? We say that we can share these reserves machines. Because when you share reserves machine, there is no issue of breaking the isolation. They're just sitting there, not doing anything concurrently. No problem. So we pre-allocate. We allocate multiple services on every physical machine, but at a single time, they only run a single virtual machine. So if previously, if you want to keep isolation, a single physical machine can run one service immediately because it's ready, and any other service after allocating it, so taking down the currently running service, loading the new service, and running it. So either immediately or after a long time, we say let's do something in the middle. Each physical machine can immediately run one of two services, or after a very long time, other services. But suddenly this machine is closer to more than one machine, to more than one service. So now it looks like this. The circle means that this is currently running on the machine. So on physical machine 1, we have pre-allocated both VM1 and VM2. VM1 is running, VM2 is just lying there, sitting. And if you have queries for service 1, you cannot forward it to physical machine 1 because it's not running it. You have to forward it to physical machine 2, which is also denoted as PM1, I see. But that's physical machine 2. Now, in this preliminary work, we're going to use a greedy slack factor preallocation, which is, again, fairly straightforward. So we, again, over-allocate by a factor of alpha. Like before, same approach, only this time, this alpha can be multiplexed. So you have several machines holding together different VMs. We call the number of VMs on every PM the pre-allocation factor. So a pre-allocation factor of 2 means you can have 2 VMs on every physical machine. Now, the greedy slack factor pre-allocation works in 2 phases. In phase 1, you try to run the machines that you need. Again, greedy. In phase 2, you try to allocate the machines that you need according to the slack factor chosen. It looks like this. We have 4 machines here, a workload of 2 VM1s and 2 VM3s. You don't need VM2 and you don't need VM4 currently. Now you start running the algorithm, and you keep doing iterating through the services until you're done. So for each service, first of all, you stop all the machines you don't need. So for VM1, we need 2 virtual machines. We can't do anything because they're all running. So we go on to VM2. For VM2, we don't need any machines, right? So we can stop using physical machine 2. We keep it allocated. It's greedy. We keep it allocated, but we stop running it. For VM3, we need 2 machines. Can't do anything. The other machine with VM3 allocated is already running VM4. So we move on to VM4. Again, we don't need any machines for it currently, so we stop using it. Now we go back again to VM1. Now VM1 can start using PM2, and VM2 can start using PM4. So after 2 iterations like this, we're done. Now we run another iteration. We see that no progress is made, and so we finish the first stage. Phase 2 is allocating machines according to the required preallocation factor, to the slack factor, sorry. So here we have again 4 machines, 2 of them denoted PM1. We chose a slack factor of 2. So we need twice as many machines for every virtual machine. We'll start again with VM1. So VM1 has 4 allocated machines. The workload is just 1. So we need 2 machines, so 2 of them are unnecessary. Now here we don't deallocate them. We keep them allocated, we just mark them as unnecessary for VM1, colored black here. Next we go to VM2. VM2 needs 1 machine. So we can allocate it over here. You see that there is a free slot. We put it in the free slot. Next we go to VM3, which doesn't need any machines, so we mark it as redundant. And then we go to VM4. VM4 needs, the workload is 2, so it needs twice, so 4 machines. So now we allocate instead of the tagged VM. So we, again, greedy. We currently don't need this VM3 for the required preallocation factor. We tag it as unnecessary, and then when we see that VM4 is missing, we place it instead of the unnecessary VM3. Now the stage is almost done, but we're still missing 2 machines for VM4. So at this point, we iterate here again. We see that we can't do anything with the machines we have. So we boot 2 new physical machines, and we start the allocation of virtual machine 4, or of service 4. Now allocation takes time. These are yellow. It's going to take a while until they're allocated, and you have to keep monitoring the load and run the algorithm again when the load changes. So this is greedy, a very direct algorithm, and we simulated this. Again, we concentrate here on flash crowd behavior. This has from analysis from flash crowd behavior on accesses to sites. It's more or less monotonic increase, lasting about between 10 and 30 minutes in these studies. Then it stays steady for a while, and then decreases exponentially until going back down to the regular load. So the regular peak to average ratio is about 1.5 typically, and when a flash crowd arrives, it jumps to be 10 times or 200 times as much. We used here 50 services. The regular workload is normally distributed with an average of 4, and the spikes go up to 80. So a peak to average ratio of 20. And we have it sort of symmetric, so about 30 minutes to go up, 30 minutes steady, and then 30 minutes until the exponentially drops back to the stable state. And we have here three services, and we see that their load is usually down here, and then goes up and then back down. I didn't put all the 50 because it becomes sort of cluttered. For the simulation, it happens about once or twice a day, and this is over 50 hours. Now, the algorithm, just described, it runs every 5 minutes. We assume allocation time is 10 minutes. We have to assume something. Switching and deallocation, so clearing a machine time is negligible. And this is a key point now. We choose a target overflow. So the maximum ratio of workload that we allow the simulation to spill over, to be not able to respond to. And what we do is we run the simulations multiple times and find the slack ratio for which we obtain this target overflow. And run it again and again. And when we find the point where the overflow is 1%, this is the simulation we take. So these are the results with classical here is the just one preallocation factor. So no preallocation, just have one physical machine running one virtual machine. Isolation, but no multiplexing. And then we have factor 2 preallocation and a factor of 3. And you see a drop off of 35%, both the average and the max, when you use just 2 preallocation, and a drop off of 50% in the average and in the maximum number of machines used if you have 3 preallocation. And this is the total number of machines in the data center simulated. So this means if we look at the maximum, that we can reduce, by using preallocation, we can reduce the number of physical machines in the data center by half, or by 35%. Smaller data center, or a thinner cloud, if you wish. Now, some practical considerations. First of all, the slack factor choice. We see that we can choose the slack factor automatically, or not automatically, but offline here, so running again and again until we find the correct slack factor. Of course, in reality, you can't do that. You have to be ready in advance without knowing what's the workload going to be. So we need some sort of prediction to realize what you would need. And the challenge is that there are others running on the same data center, and they have their own prediction, and they also need to pre-allocate on these same machines. So you have some competition. This goes directly to billing. If you have some customers, the customers can tell you, I want to be pre-allocate. I want 5 times the number of machines I currently have. Or they can tell you that with 99%, I want to be able to run the workload that's incoming. There's a question of how to do the billing here. This also applies for private clouds. You need to balance between your different services, even if you're running alone. And finally, there is the load balancer implementation. We did not address this here, but this is very dynamic, and the load balancer has to be very efficient in directing the queries to the correct physical machine. Now, the next step with this is first considering the algorithm for deciding which machines to allocate where. We compared here apples for apples, a simple algorithm without preallocation and a simple algorithm with preallocation. But we should probably use very sophisticated algorithms for both cases. And the question of which virtual machines or which services which we should co-locate is not a simple one. It's not bin packing. We couldn't find a matching variant, and there are many of these. and it's not expert team formation where you need to choose the machines to answer your current load. You need to choose how to build the machines so that they will be able to answer incoming loads in advance. Additionally, there is the issue of using the full spectrum of preallocation. You can have middle ground between not preallocated and completely preallocated. You can store the image but not boot the machine and so on. And we'll skip through the rest of this because I'm out of time. And with the summary hanging here, I thank you.
Hey, Zsoltis from ETH Zurich. So my question is related to the examples that you give, and I looked in the paper. So you always assume at most two virtual machines per physical host. So where does that limitation come from? Or is that just an arbitrary number that you use in your examples?
We use the two preallocation and three preallocation, and these are arbitrary numbers. The actual numbers have to be determined by the resources available to these machines. In these environments, typically RAM is the most critical resource. So you don't want to have many machines staying in RAM waiting. There's also the issue of hard drives. You can only have so many virtual machines pre-allocated or preloaded on your hard drive. We had to choose some number to perform the simulation. The actual numbers really depend on the exact hardware you have, and the operator, the cloud operator, needs to decide how much preallocation is going to help him, because at some point it's not going to be worthwhile to preallocate more machines. You're going to spend a lot of money on storage, and the benefit is going to become lower. The exact number really depends on the workloads and on the costs of the specific elements.
May I have a follow-up to this? Okay, just so that you mentioned that these preallocated machines would also stay in memory. So this is what I also was thinking about. Is it so at the beginning you speak about security, and then people not really wanting to share the physical machines with other guys' VMs. So do you see any kind of conflict here with, by pre-allocating, actually, could you end up in a situation where you compromise security of...
That's a good question, and the answer is that one has to draw the line somewhere. So when you just pre-allocate on the same machine, you are exposed, we believe, to the same danger of just running in the cloud with someone else. If you are indeed willing to run in the same cloud, not in the same machine, but in the same data center as other customers, then it should be just as safe for you to lie dormant on the machine that the other customers are running on. If they do obtain control and the hypervisor and break out of their memory, then you're in trouble wherever you are.
Okay. Well, thank you. I think I will grab you for a coffee later.
Any other questions? Yes, please.
Do you have a sense as to how far your two-phase algorithm is from the optimal?
No. This is the exact follow-up work I was referring to, realizing how well we can do. Just shortly, I'll say that this really depends on the exact workloads, because in general you can find like adversarial situations where pre-allocation is not going to help you at all, because you just set the workload such that you gain absolutely nothing. So you need some assumptions on your workload, empirical or other, and then we might be able to answer this question.
Yeah.
Konrad Müller from Karlsruhe. I'm wondering, in your model, what you
Okay, so implicitly, we only addressed here stateless or soft state services.
So you would just clone
And
the VM.
yes, and even for these services, many clouds, in the common clouds, it takes quite a while to start up a new machine because of the cost of getting your image off storage and running it.
But you don't have to get the storage, that's my point.
Um,
You just clone the memory content of one VM to another machine, and then say, okay, the image comes from NFS. When you need anything else, take it from there.
Yes, from the clouds we have seen in most cases and in practice, they do require longer than that. Although I agree with you, and some providers achieve far better performance. The fact is that in most clouds we're just not there yet. That being said, there is the issue of running other services that have a caching module or even storage. So really stateful VMs, where the cost of starting a new VM is much higher.
Yeah, but your standby VM would sleep anyway, so it wouldn't have a current cache footprint. So
Exactly,
same problem.
exactly. This is something that we're not sure that we can address directly with this, and there is a big question of how we can expand this to have the VMs ready to start faster.
Very quick.
So it seems like you're basically building like a cold grain scheduler, and because you don't trust the hypervisor when it comes to resource sharing now.
Yes.
In my experience, I mean, at least with ESX, we have a pretty strong story when it comes to resource management, and I'm wondering, like, what is the resource sharing scheduler that you feel is missing in other hypervisors? Like, your experience with IO schedulers out there that you feel are lacking feature, and that pretty much get you to go to this cold grain scheduler.
And the thing is that at this, using this sort of scheduling is so coarse that you get very strong isolation. If you get lower than that, then the question of isolation arises, and the schedulers or the hypervisors try to achieve perfect isolation, and when they reach that point, you won't need to use this coarse method.
I guess,
But in general, you're right.
I mean, I guess I'm saying, like, if you have a good enough, I mean, a strong enough CPU scheduler, one of the many resources, in your data path, in your hot path, effectively, this becomes less necessary. I mean, except if you have a resource concept that span multiple hosts, and but I was more wondering if in the schedulers that you see out there today, if you see
This.
feature missing as well.
Okay, I think this is not at all the issue that we were addressing. The schedulers, CPU schedulers, is not what we address. We want to just avoid the machines running together, due to security issues and performance not on the CPU but contention on I/O bandwidth, for example.
Well, I mean, you have multiple schedulers. Okay, I mean, I guess we can take that one. I mean, for the security standpoint, I can understand that, I guess. That's okay.
The fact is that customers are reluctant to often. I mean, it depends on the sensitivity of the service you're running, but with high sensitivity applications, both performance-wise and security-wise, customers are often reluctant to run together with other customers.
Okay, thank you. Let's close the
Thank you.